Welcome back. In this video, we're going to take a look at density and particularly how we can do some calculations that can give us a value for density. So definitely review the notes that I have available for you online, or just look up density and figure out what it is. And will notice that there's a couple different ways to measure it, but the measurements actually they still have the same meaning, but there may be some difference as to like the accuracy or precision of it, and that's what's important. So keep in mind density, what type of property it is, and how to measure it. Uh, let's just go ahead and jump in. I've got a couple of practice problems for you where we take a look at the methods on how to do that. We'll be doing stuff like this in the lab. And these are a really good exercise on how to really focus on accuracy of measurement, how precise your measurements are, and then manipulating significant digits, which is always everyone's favorite. So let's go ahead and jump in. All right, measuring density. Welcome back, class. Let's take a look at measuring density of matter. And there's really two ways to do this. We either have something where we can take some geometric measurements and then do some calculations, or the classic displacement method. Let's jump in and take a look. All right. So here we go. We've got a tool. So that little blue circle there just sort of represents some sort of, well, spherical object, right? Let me get a color. What color do I like for? We'll just stick with blue. It's the classic. So we've got this spherical object right here, right? And what we want to know ultimately is what is the density for this object here, right? That's what we want. That's what we need to know. So we know density is equal to mass divided by volume. So let's take a look at let's list out all of our variables. It wants to know what's the density, so automatically we do this. Mass, well, we're given mass here, so it's 4.880 grams. And we need volume, and that is a capital V. Volume is a capital V. And then lowercase m in this situation is mass. And there's no volume listed up here, which means we look at this and we realize we're going to have to do some measurements and do some calculations ourselves. Okay, so what we do is, if you imagine this was not here and this caliper were closed all the way, then no matter what, wherever this zero line is, you just follow it and you just go up from this zero line and you take a look at where you are on your scale. Okay, wherever you are on your scale, like right now we are right here on this part of the scale, so that's where we're going to measure. Okay, if this thing were closed all the way, this zero line would line up directly with this zero line. Okay, and we're not using the scale up top because we see how this says inches, and so the top unit, we're not going to be using that scale. We're using the metric unit. And so now down here it shows 10 and then 20. We see here this little thing that says millimeters, and so we begin to think, well, that kind of makes sense. Up here is 1 inch, and there are about 2.54 centimeters per 1 inch. So if you look at this 1 and you come straight down, you can see that this line is slightly to the right of that line right there, which means it's about halfway actually between there and there, just about halfway. Well, that means if you think about if you think about this right here, what's listed here, and knowing that this is an inch and that 2.54 centimeters equals, or 2.54 centimeters equals 1 inch, then that must mean that right here, this is 1, 2, 3, 4, 5 millimeters, 6, 7, 8, 9, 10 millimeters. So this is 1 centimeter right here. This is 2 centimeters. This is 3 centimeters. This is 4 centimeters, and so on. So we can look at this and we realize that this is 2 centimeters right here. This is 1 centimeters. So this would be 1.5 centimeters. If we come up here, this would have to be 1.6 centimeters. And so far, looking at that spot right there, we can see that, and I'm actually going to use, I actually do want to use a different color so I can really showcase what I'm talking about here. So here, actually black's going to be really good. So from this side to this side, all of this right here. Okay, I'm actually going to come up more. So from there to there, all of this right here, from here to there, we see that this is 1 centimeter, 1.5, so it looks like it's 1.6, and it's directly on the 6, so our estimated digit, remember we have to have that estimated digit, so it's 1.60 centimeters. Okay, 1.60 centimeters. So now that still doesn't tell us volume. That just tells us this measurement here. So now we have to we ask ourselves, what else do we need to know? So all of this is our given information. Okay, all this is the given, all the information. So step one is always figure out what are you given. And a word problem is just a real life situation. You know, you're somewhere and you're looking at something and you're just thinking about what you need to do. The second thing is we need to, obviously we have two unknowns. Well, we have two unknowns, which means if we're trying to figure out what density is, we have to figure out how to calculate volume. So number two is we have to determine how to calculate volume. Okay? How are we going to do that? Well, this is a spherical object, and you can look this equation up, and you know that the volume for a sphere is 4/3 pi r cubed. All right, so the second thing is we obviously knew we were going to have to measure this because the picture shows that, and we could have this in real life. So now we look at this and go, okay, well, 4/3 pi r cubed. Well, this entire distance here that it was measured, this is the diameter, lowercase d, right? So now you've also learned that diameter equals 1/2 of the radius. And why is this important? Well, we're given diameter, and this equation here has radius in it. So if we can solve for, oh, I'm sorry, I said that backwards. I get ahead of myself sometimes. These things happen. The radius is 1/2 the diameter. That makes much more sense. It happens. It happens to all of us. Sorry about that. So 1/2 the diameter. So if we solve for the radius, check. Then we could put this information in here, solve for volume, check. Then we could put that information in here, check. We'd have everything to solve for density. So let's do that. Well, let's go to a blank piece of paper. So up here we've got our volume equation. All right, I'm just going to rewrite all this. We've got volume equals 4/3 pi r cubed, and then we have radius equals 1/2 the diameter. We know that our diameter is the 1.60 centimeters, right? So radius equals 1/2 of 1.60 centimeters, which is going to be 0.800 centimeters. Now I want you to stop for a moment and ask yourself, why did I write 0.800 centimeters? I'm just going to give you a second to think about that. If in your mind you thought, well, 1.60 has 3 sig figs, so I need 3 sig figs here, there's one, and there's one, then you would be correct. All right. Give yourself a point if you did that. All right. So we have the radius. All right. So now we can come over here and solve this equation. So we've got 4/3 pi, and the radius is 0.800 centimeters, and then that's cubed. So we've got 4/3 pi. All right. And then take out your calculator and go 0.8 times 0.8 times 0.8. Right? That's the same as saying 0.800, right? And so in the calculator, what you get is 0.512. All right. Now, what we really did was 0.800 centimeters times 0.800 centimeters times 0.800 centimeters. So that means we multiplied this number, and this number. But that also means you went centimeters times centimeters times centimeters, all right, which will give you cubic centimeters, okay? Gives you cubic centimeters. Just like x times x times x is x cubed, right? Same thing. All right, so now we have 0.52512 in our calculator. So now we just go times and then pi, use the pi button, times, and then put in parentheses 4 divided by 3. All right, time divided by 4/3. And you should get 2.144660585. I'm writing everything that I got so we can learn from this. All right, you don't need all these numbers. Up here we have 3 significant digits. We started off our measure value here, 1.60, 3 significant digits. So with what we're measuring, it makes sense that we need 3 significant digits. Well, there's the first 3 significant digits right there. And this 4 will not round that up, so we get 2.14 cubic centimeters. So now we know volume. We now know that the volume equals 2.14 cubic centimeters. Now we have everything to solve for density. So let's just go back to our other screen and let's solve for density. All right. So we know our mass is 4.800 grams and our volume is 2.14 cubic centimeters. All right. So let's go ahead and let's do that. So we're solving for density. And the mass equals 4.880 grams. The volume equals 2.14 cubic centimeters. And you know what, actually, I want to show you something that will help you get even better answers. You see how this 4 does not round this 4 up, so 2.14 works. But there are other numbers. So this is 2.1446. So like all of this, like this 6 could round that 4 up and that could be a 5. This 6 could round that up again, which would round that up again. So it's never a bad idea when you're doing your calculations to use some extra numbers. So it's never a bad idea to go one extra number when you're doing your calculations and then round up at the very end. And so let's go ahead and use this. There's 4 sig figs right there, right? But that's just extra numbers. Okay. So let's add that 4 in as well. This will give us a little bit more accuracy, or a little more precision in the calculation. All right. So now we have density equals mass divided by volume. The mass is 4.880 grams, and our volume is 2.144 cubic centimeters. All right, so now we've got 4.880 divided by 2.144. We should get 2.276119, and there's a bunch of other numbers, but I'll go ahead and write them, but you just need to write extra numbers, okay? You just need to always write extra numbers. Now we look at this. We've got grams over cubic centimeters. And none of that cancels out. So the final unit stays grams per cubic centimeter. It stays that way. All right. So now let's go back to the original problem. This number here has 4 significant digits. This number here has 3 significant digits. When you multiply and divide, you want the least of the numbers that were measured that you started with. 3 is less than 4. So what we're going to do is go 1, 2, 3, and this 6 will round that up. That's 7 up, so that's 2.28 grams per cubic centimeters, and put a box around it. There's our final answer. The density of this make-believe object is 2.28 grams per cubic centimeter. What that means is there's 2.28 grams per every 1 cubic centimeter. So if you had 2 cubic centimeters, you would have twice that mass because you have twice that volume. All right, it's just so like your math teachers have taught you this. You know, since this is fixed, if you had twice the mass, it would be 2 times this number and 2 times that number. You would have twice the mass and twice the volume. But it would still equal out to 2.28 grams per cubic centimeters, right? Okay. So there's how you do, that's just a geometric calculation with a spherical object. If you had something that was a cube, then, all the sides are the same. They measure the same, so it would just be side A times side A times side A, right? Or if you had a rectangle, it'd be length times width times height. It just depends on what your shape is. I just happened to pick a circle just because I wanted something to show you how to do a little more of a complex problem. So what you see here, all of this is what you would do to get credit. You would list out your given information. You would list out the steps you need. You would show your work for solving those steps. Then you would show all of your work. So notice I showed all of my work. Didn't take any shortcuts. I have units with numbers. It's all there. All right, and your math teachers have taught you this, so make sure you follow that. All right, so now let's take a look at one other example. So let's just say, so this is 4.880 grams. I left it the same mass. We're just going to leave it the exact same mass. Why? Why not? Okay. So now, what we want to do is with this figure out what in the world is happening here. So you can see here that there's a water line. This graduated cylinder is empty. This object was obviously placed in there, and then the water level rose. Okay, and so the difference right there, that the water level rose, that entire difference, that's actually, that yellow is really hard to see, isn't it? I'm going back to purple. I like purple. The difference that rose right there from there to there, that is the amount of displacement. It's the amount of displaced water, which equals the volume of the object. Whatever you put in there, whatever that is, it doesn't matter what it is, it's just an object, okay? So we're still doing the whole density equals mass divided by volume thing. And so density equals, we don't know, mass equals the 4.880 4.80 grams, and then volume equals whatever we figure this out to be. So let's go ahead and let's zoom in. Let's zoom in a little bit so we can see this. All right, let me zoom this in for you. So right there, that spot right there, that's our meniscus. So here is the initial meniscus reading, and then right here, and notice it's not on this line. It's between this line and that line. Right there is where the meniscus is after the water has been displaced. So we need those two readings right there. We need to know what this is, and we need to know what that is. And the difference will be the volume. All right, so if this, so we got to figure out our scale. If this is 100, and there's 1, 2, 3, 4, 5 gets us to 200, we have to figure out what each of these are. So it makes sense this is 20 if there's 5, right? Because 5 times 20 is 100. So 120, 140, 160, 180, 200. So we've got that figured out. So each of these lines is a value of 20 milliliters. So the initial volume right here, that's 200. Right here, this is 220, 240, 260. There's 280. So right there, that must be 270. Now the unit, it shows cubic centimeters, right? It shows cubic centimeters. And this is where we can learn a little something new if you don't already know this. Cubic centimeters, okay? Cubic centimeters is the exact same as a milliliter. So 1 cubic centimeter of water equals 1 milliliter of water. Those two units are interchangeable. They are the same thing. We tend to say cubic centimeters when we are talking about geometric measurements, and we tend to use milliliters for graduated cylinders, things with liquids. All right, so that'd be easy to remember if you struggle with this type of stuff. All right, milliliters. There's an L there. So if we're working with liquids, then we're going to use the milliliter unit. So right now this is in cubic centimeters, but I'm going to write it as milliliters. Okay. So now what's the difference between these two? The difference between these two is 70 milliliters. So I know that 70 milliliters is the volume of that object. All right. And notice I wrote 70.0, right? Because remember we've already had these lessons. If I don't put the decimal, that 70 would be 2 or an infinite number. So you always add a decimal and at least 1 0. So now density equals mass divided by volume. So we've got 4.880 grams divided by 70 milliliters. All right, take out our calculator. We've got 4.880 divided by 70. You should already see that you are going to get a smaller value. It's because you got a much larger denominator, right? So that's 0.06971426. You don't need all these, but I'm just writing the extra to help you learn how to evaluate your answer. Then you come over here and you notice we got grams per milliliter. It says grams per milliliter. 4 significant digits, 3 significant digits. 3 is less than 4, so we want the first 3 significant digits. And then we want to ask ourselves, does the next number round it up? A 1 does not. So the final answer for this is 0.0697 grams per milliliter. All the work that we did on this page, oh, I'm sorry, that's this problem. All the work right here is how you would get credit for this problem. Okay? And so just one thing that I want you to take away from this is that grams per cubic centimeters is the same as grams per milliliter. They are the exact same unit. So here's an easy way to remember this. A bunch of you have gotten a shot before. Matter of fact, we all have. We've all gotten a shot before, and if you think about it, those shots have this scale on it. And that scale right there looks a whole lot kind of like something like this. So this is your syringe. Right, there's the plunger. And then, you go to get a shot and they always say, hey, give them 5 cc's of this. And so the question is what's a cc? Well, let's think about it. Cubic centimeter. So a cubic centimeter, and notice there's a liquid in here. You don't look at that and there's a bunch of geometric shapes in there. It's a liquid. So cubic centimeter is the same as a milliliter. That's why these two units are interchangeable, because cubic centimeters equals a milliliter. So both of these units are the unit for density. Okay. It was all right. Good learning with you. Do your practice problems. Check in with me if you have any questions. I hope this helped. This hopefully should have cleared this up a little bit. Displacement method. You just have to get the difference in the volume measurement with the initial and the after. All right, before and after. With the rise of water. And that rise of water will be your volume. Then plug everything into your density equation. And then when it comes to a geometric shape, you just need some sort of tool in some way that can measure the dimensions that you need. In this case, we just had to measure diameter so we could get radius, and then from there we could just plug it in and do our calculations. Just depends on the shape, depends on which calculations you need. Okay. All right, review all this work, and I hope this helped. And that's it. Measuring density, it's really not difficult. Depends on the type of object, so you can use the displacement method, or you can use three-dimensional measurements. All matter is that we're going to be manipulating. It has 3 dimensions. You have 3 dimensions. Atoms have 3 dimensions. More specifically, we could get into that. So, but there's times when your object is shaped more geometrically, which we sometimes call like a regularly shaped object, and then you can measure those 3 dimensions. And then remember from math class, if something is spherical, a circle, that you would use a different equation for that. If it's rectangular or square, you're using length times width times height, whatever the case might be. And then, of course, if it's square, all the sides are the same, so basically it's just whatever x or a or whatever you want to call that side is, right? But then if it's irregularly shaped, it's hard. You cannot definitely measure 3 sides and get measurements that make sense, because there's spaces and there's pockets and there's parts where the matter is not there. And so what you do for that, as you saw from the example, is you place that in water, and as soon as you place the object in water, your water level is first here. Whatever that level is that rises up has to be the amount of space, volume, that the object is taking up. It's just like getting into a bathtub, right? So these are concepts that you're very familiar with, but the people tend to take shortcuts with their with the calculations, and then you punch numbers into a calculator and you get this huge string of numbers in the calculator, and you're not sure how many of those do I write. How many of these numbers do I write down? And so typically before high school, a lot of times you're taught just 2 places after the decimal, and that's okay in some situations, but as you've seen from what we've been doing here in this video and the problem sets that you've been working on, that's not always the case. That's not always accurate and doesn't give you precision with your measurement. So significant digits, you're always going to want to be doing that with everything that you're
you're doing. All right. Hope this helped. It was good seeing you. I'll see you again later for another video. Bye.